Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Time to enter the world of civil engineering. Here we will learn about different concepts related to civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about structural analysis, shear, and moment in a beam. Introduction. The term beam refers to a slender bar that carries transverse loading, that is, the applied force are perpendicular to the bar. In a beam, the internal force system consists of a shear force and a bending moment acting on the cross-section of the bar. The shear force and the bending moment usually vary continuously along the length of the beam. The internal forces give rise to two kinds of stresses on a transverse section of a beam. Normal stress that is caused by bending moment and shear stress due to the shear force. Knowing the distribution of the shear force and the bending moment in a beam is essential for the computation of stresses and deformations. Here, we will learn about the shear and moment in a beam. As we know, a beam is a properly supported structural member capable of withstanding loads that are applied in a direction perpendicular to its central axis. Here, we are going to discuss about type and nature of the forces internal to a beam. Consider a cantilever beam, subjected to a concentrated load at its free end. Suppose we conceptually cut the beam at its midpoint. Choose to examine its right segment. Since the condition of equilibrium must be satisfied for the segment, that we can write sum of the forces in the x direction must be 0. Summation f x equals 0, sum of the forces in y direction must be 0. Summation f y equals 0, sum of the moment about point K must be 0. Summation m c equals 0. Here, the first equation is automatically satisfied, since there are no applied load in the x direction. But, how do we satisfy the second and third equations? A downward force P is applied to the right end of the segment to satisfy the second equation. Therefore, there must be an upward force at point C equal in magnitude to P in order for the sum of the forces in the y direction to be 0. This upward force labeled V on the diagram is called the shear force. It is one of the internal forces in the beam. To satisfy third equation, it is important to recognize that P creates a bending moment about point C. The moment has a magnitude of P times L/2, and a clockwise direction. For the sum of the bending moment to be 0, there must be a bending moment at C. See figure. The magnitude of this moment must be equal to the magnitude of the moment that P that creates about seeing the two moments. However, must act in opposite directions in order for their sum to be 0. Let us denote the bending moment at point C as m. Here are the two equilibrium equations in terms of Van M summation F, y, equals V, minus, P equals 0 equation 1, summation M, C, equals M plus, PL slash 2, equals 0. Equation 2. Solving for the two internal forces, we get V equals P and M equals negative P times L over 2. As V equals P from equation 1, M equals minus PL slash 2 from equation 2, here, we can conclude that when a beam is subjected to a transversal load, a load that is perpendicular to the beam's central axis, then two internal forces develop in the beam. A shear force and a bending moment. Generally, these forces do not remain constant in the beam. Therefore, their value need to be determined at critical location throughout the beam. In order to calculate the shear force and bending moment at a point in the beam, it is necessary to conceptually cut the beam at that point and draw the free body diagram for each segment. Here, it is important to recognize that any time we cut a beam, we need to show the beam's internal forces at the cut point. So, if we cut this beam at its midpoint C, here, we end up with two beam segment, left segment and right segment. The internal force at point C in the left segment of the beam are showing in figure below. In the right segment, forces are like that as shown in figure. Note that at C the shear force in the left segment has the same magnitude as the shear force in the right segment. We are using the same variable V to denote the magnitude of both force vectors, however, they do have opposing directions. One is draw upward, the other one is downward. This is necessary as the algebraic sum of two vectors must be 0. The same is true for the bending moment at C. The moment in the left segment is drawn in counterclockwise direction and in the right segment it is drawn in clockwise direction. Since they both have a same magnitude, the algebraic sum therefore is 0. Now, let us see how we can actually calculate shear and moment at a point in a beam. The procedure is rather straight. 1. Calculate the beam. How to calculate shear force and bending moment in a beam. Calculate the beam's support reactions. 2. Conceptually cut. Calculate the support reactions. Cut the beam at the point of interest. Show the internal forces at the cut point and draw free body diagram. Formulate the equilibrium equations for either the left segment or right segment of the beam. Solve the equations for the unknown shear force and bending moment. To understand this concept, we will do this using an example. Suppose we have a simply supported beam, subjected to two concentrated loads. Determine shear and moment at point C and D. Let us start by calculating the support reactions. Let us draw the free body diagram. Here are the equilibrium equations. Summation F x equals 0a x equals 0. Equation 1, summation F y equals 0a y plus b y minus 4 minus 2 equals 0. Equation 2, summation m a equals 0. 4 times 8 plus 2 times 12 minus 16b y equals 0. Equation 3, from the equation 3, we can calculate 32 plus 24 minus 16b y equals 0. 16b y equals 56 b y equals 56. 16 equals 3.5 kilonewton kN. From equation 2, we can calculate a y plus b y minus 4 minus 2 equals 0. A y plus 3.5 minus 4 minus 2 equals 0. A y equals 2.5 kilonewton kN. From equation 1, we get a x equals 0, hence, we get a x equals 0a y equals 2.5 kilonewton kN b y equals 3.5 kilonewton kN. Graphical representation of these value on the beam. Now, determining the shear and moment at point C, we cut the beam at C and draw the free body diagram for either the left segment or right segment, whichever is more convenient. Let us picking the left segment dot and drawing the free body diagram of the left segment. Note here, we did not draw the internal axial force at C since I already know, there is no axial force in play here. How? Because there is no applied force in the x direction. The relevant equilibrium equation. Summation F y equals 2.5 v C equals 0. Equation 4, summation m a equals 0 4 times V. C minus M C equals 0. Equation 5. From equation 4, we get Vc equals 2.5 kN, Kn. From equation 5, we get 4 times 2.5 minus mc equals 0, m c equals 10 kilonewton meter. Here is the result shown in the beam. To determine shear and moment at point D. Now, cut the beam at point D and draw the free body diagram for either the left or the right segment. Let us pick the right segment. Let us draw the free body diagram. Again, there is no axial force present on the beam. Now, omitting the internal axial force at point D, then the relevant equilibrium equations are summation F y equals 0 V D minus 2 plus 3.5 equals 0. Equation 6. Summation M V equals 0 M D plus 6 times V D minus 2 times 4 equals 0. Equation 7. From equation 6, we get V D equals minus 1.5 kilonewton, Kn. From equation 7, we get M D plus 6 times dash minus 1.5 minus 2 times 4 equals 0, M D equals 17 kilonewton, Kn. Here is the graphical representation of the loads on the beam. Now let us solve another example. Suppose we have a cantilever beam subjected to a uniformly distributed load, UDL. Let us start with a couple of algebraic equations for calculating shear and moment at any point in the beam. Let us write an equation in form of V, x, where x is the position of an arbitrary point in the beam. When I substitute a value for x in the equation, it gives me the value of shear at that point. I also want to write a similar equation for the bending moment m, x, in the beam, which can be used to calculate internal bending moment at a desired plant. In other words, I am interested in representing shear and moment in the beam algebraically. To do this, let us the support reactions. Let us draw the free body diagram of the beam. Here are the equilibrium equation, summation F x equals 0a x equals 0. Equation 1, summation F y equals 0a y minus 500 times 10 equals 0. Equation 2, summation m a equals 0 m plus 500 times 10 times 5 equals 0. Equation 3. Solving these equations for unknown, from equation 1a x equals 0, from equation 2a y equals 5000 Newton, n, from equation 3m equals dash, minus 25,000 Newton meter, nm. Now, let us cut the beam at an arbitrary point, say point P. Draw the free-body diagram of the left segment of the beam, since we do not know the length of the segment, where z is the distance from the left end of the beam to the point. Write the equilibrium equation in terms of x. We have sum of the forces in the y direction must be 0, that is 5000 minus 500 x minus v equals 0. Minus 500 x is the area of distributed load applied to the segment. The rectangular load has a height of 500 and a base of x, therefore its area is 500 times x. Sum of the moments about point A must be 0. Therefore, v x m plus 500 x x/2 minus 25,000 equals 0, just like the first equations here. 500 times x is the area of the rectangle representing the distributed load. X over 2 is the distance from the center of the area to point A. Hence, the product gives the moment of the distributed load about point A. Solving these equation, in terms of x 5000, minus 500, x, minus v equals 0, v, x, m plus 500, x, x/2, minus 25,000 equals 0. On solving we get, v equals 5000, minus 500, x, m equals 5000, x, 250, x, 2, minus 25,000. See diagram. So these are the shear and moment equations for the beam. V equals 5000, minus 500, x. M equals 5000, x, 250, x, 2, minus 25,000, where 10 greater than or equal to x greater than or equal to 0, we can use them to calculate shear and moment at any point in the beam. For example, Case 1. What is the shear and moment at the left end of the beam where x equals 0? At x equals 0, v 0 equals 5000 minus 500, 0 equals 5000 Newton. VOF 0 equal 5000 Newton. At x equals 0. M 0 equals 5000, 0, 250, 0, 2, minus 25,000 equals minus 25,000 Newton meter. Notice that these are support reactions. The equations correctly gives us the support reactions for shear and moment, when x equals 0. Case 2. What is the shear and moment at the midpoint of the beam, where x is equal to 5? Hence, V 5 equals 5500, 5 equals 2500 Newton, M 5 equals 5000, 5 minus 250, 5 to 25,000 equals minus 6250 Newton meter. Case 3. What is shear and moment at the free end of the beam, where x is equal to 10? Hence, V 10 equals 5500, 10 equals 0, M 10 equals 5000, 10 minus 250, 10 to 25,000 equals 50,000, 50,000 equals 0. The equation correctly indicates that the shear and moment at the free end of the beam are 0. The design purpose: it is generally useful to graph these equations. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.